All right, this video is either as a pre-lab for lab 1, calculating speed and determining velocity for mission 2 or expedition 2, or it is to be used as a post-lab to help you complete the lab. Either way, you can watch it either before or after and it'll help you. All right. Now, one of the things you're going to need to do is measure and record the length of the foam track. And you need to make sure that when you measure the length of the track, that it is flat and not curved. So if you look over here in this particular picture, this is a curved track. So if you were to measure its distance there, one, it'd be difficult, and two, you probably wouldn't get a very accurate measurement. So you want to make sure that it's laid flat on the ground or on the table, and that you measure it to get the distance that way. Most likely you'll get the answer in meters. And then go to probably to the nearest centimeter. So it'd be probably something like 7 meters or 7.25 meters. Then you'll arrange the foam into a track using books and other objects to create hills, shown in figure B, which you see up there. And then you, after you've done that, you're going to test the track with each one of the balls to make sure that it'll stay on the track and stay on there. Then once it does, you need to record the mass and a description of each ball that you will use in this lab. The ones that you're going to use a small pool ball, a small metal ball, a small plastic ball, and a small cat eye ball. That's the one called a cat eye marble. And then you'll need to record the mass, and it doesn't specify, but we will be measuring the mass in grams, right? And so in your data table, you need to put that down, either that or label grams every single time you measure it, one of the two. Then you need to stretch a piece of string from the start of the track directly to the barrier at the end of the track. Measure the string to determine the magnitude of the displacement from the beginning of the track to the end. Now, displacement is different than distance. Why? Because it's a vector quantity, not just a scalar one. Displacement has a magnitude and a direction, right? So something like distance, you could say 5 meters, but if you were going to measure displacement, it would need to say 5 meters right or 5 meters east, and it'd have to have that. Now, how are you going to do that? Well, as a quick diagram, I can show you here. Let's say your track starts up high, comes down, has a bump or two in it, and then comes down and finishes. All right. In order to measure the displacement, you'll need to measure from this point, then take the string and pull it straight and tight all the way down to the finish of the track right there. And you'll just be measuring the length of the string, because that, if you can envision, is the vector of displacement from point A to point B. Notice it'll be less than the distance because there won't be any curves in it. All right, so you'll need to have that measurement as well. Then we go on. You're going to put down the time trials for each of your trials. You'll need to do each one 3 times. So ball 1 in this case is the pool ball. It won't matter what order you did it in or do it in, and you'll record those values. Once you have all 3, you'll need to add these 3 up and divide by 3 to get the average time. I think you're pretty aware of that. The average time in this one is in seconds, so that needs to be listed in our data table. Either that or put it there on the end, okay? Once you've got an average speed, after you've got an average time, you're then ready to calculate speed. So here's an example on that one. Let's say we're doing ball 1. The distance of the track you measured was 7 meters, all right? And the average time that it took to do that was 3 3.65 seconds. And right here, you need seconds in this particular thing. And then we need meters here, our parentheses. So now you're ready to do the equation for speed, which is distance divided by time. So the distance it traveled is 7 meters. You need to divide that by the time, which is 3.65. When you do that, you're going to get an answer that is going to be in meters per second. All right. Now, there's the units. Because it is a derived unit, you can see that it's taking distance in meters and it's per unit of time in seconds. So when you take 7 divided by 3.65, well, it's not showing me how to change the screen. So I'll go back to this one. You could do the math and get it. I'll use a calculator off screen real quick. And if I take 7 divided by 3.65, I'm going to get 1.92 meters per second. 1.92. That's not much of a 2, but it'll work for this. All right. Now, that would be your speed in meters per second. Then notice the graph. It says graph your data. Put time on the x-axis and distance on the y-axis. Choose an appropriate scale and create a title for your graph. Don't forget, create a title. Plot the average speed of each ball as a point. Then draw a line from each point to 0, 0. We also call that the origin in the bottom left corner of the graph. All right, so we have, I've already put these on here. You'll have to write them in, but we have time in seconds on the X and distance in meters on the Y. And then it's trying to figure out a scale. I went with every 4 squares would be 1 meter. And then that gets me up to 7 meters up here at the top. And then time, I went with every 5 squares is a second. And that gets me up to 5 seconds. So if I was to graph the data from up here, I would need to graph the distance of 7 meters at an average time of 3.65. So we come over to 7 meters, which is this line right up here. And then I would need to go over to 3.65. Well, if this is 1, 2, 3 seconds, this would be 3.2, 3.4, 3.6, and then halfway, or not, excuse me, a quarter of the way would be 3.65. So now if I go up to 3.65 and 7, that's where my point would be. And then the part that you hopefully understand is then what you're going to need to do is use a straight edge and a ruler and connect this origin to your point that you have right here. And now this is not going to be perfect, but it's going to look something like that. All right. And you're going to have a line, a straight line that does that. Describe the relationship between the slope of the line on the graph and the speed of the ball. So remember, the greater the slant, the greater the slope. So a line like this, right, would have more slope. A line down here would have less slope. And you need to relate that to the speed. Based on your observations, in which area of the track do you see increases and decreases in the ball's speed? So think about how your track was laid up and discuss where you saw increases and where you probably saw decreases in the speed. The rest of the questions I think you can answer on your own, and that should sum everything up.